Okay, so let's begin. So we're going to, in this case, work on designing a recommender system that is going to be focused on a very specific task, where we want to recommend people to go to a category they have not shopped in before. And those of you who've heard of recommender systems, do you know what is the most typical algorithm for a recommender system? Like what would, let's say, some company like Netflix use? Or the concept behind it, like how would you build a recommender system for users and movies?
Use the past experience.
Yeah, so usually there is an algorithm called collaborative filtering algorithm, right? So let's say you have a bunch of movies that you have watched. The algorithm will say, okay, who are users who are similar to you? They will compute some kind of similarity, and then based on that, they will look at movies that the person who's similar to you have watched and liked, and you have not watched and liked, and they'll recommend that to you, right? So that's the very classical approach. But as you can see, if the sales is very concentrated, if people have watched only a very few movies, we can't use that kind of an algorithm, right? Because you don't have that kind of data. So that's why this becomes a very challenging problem. It has a lot of benefits for doing it. The CEO wanted to do it because prior research has shown that it's actually much more profitable to get more value from existing customers than to acquire new customers. It enhances lifetime value, and like I was saying, it also reduces the risk if you have a supply side shock. Let's say one factory, let's say gets locked down due to COVID or something. You have a more diversified set of consumption going on. So that's the motivation for this problem. Okay. So it relates to other work that has been done in the literature. I won't go into too much details. I have only limited time. But it relates to things like cross-selling. But most of the cross-selling literature is generally at the product level, and it is not restricted to sending people to new categories, like things that they have not bought. So it could be, sometimes the best thing to cross-sell is more of the same thing, perhaps, right? So they don't have this hard constraint. For us, it is going to be a very specifically hard constraint, right? So if you are, let's say, shopping in, let's say a particular category, let's say pillows, we can't recommend those to you. We're going to send you to a different category. So the whole idea is to diversify. So it's related to this. It's also related to just broader literature on recommender systems. So my colleague, Geras Adamopoulos, he has done a lot of work in this area. However, one thing to note is that traditional collaborative filtering algorithms, the most classical recommender system algorithm that's used, research has shown that actually goes opposite to what we want to try to do, right? That tends to actually recommend more popular products and actually reduces sales diversity, okay? We want to actually increase sales diversity. And there has been some other work as well to improve diversity and novelty. But one big gap in this literature, which we will do out here, overcome, is that the prior literature, they tend to follow the classical ML approach, where they will basically take the past data that they have, they will train a model, let's say on 70% of the data, and then they will test the model on the remaining 30% of the data and look at how accurate the recommender system is, right? But that does not tell us actually how what is the causal impact of introducing this recommender system, right? Because, for instance, in the holdout data approach of testing, you don't know whether the person would have, let's say you recommend somebody who's a wine drinker, you recommend them whiskey. You don't know, for example, would they have bought the whiskey anyway, like without your recommendation even, okay? So we don't have that counterfactual, so we can't actually estimate the true causal effect, the economic value of introducing this recommender system. So you'll see that's a gap in the literature that we will overcome here as well. So we will basically we will use what's known as A/B testing. You heard of A/B testing, all of you, right? So we will kind of design a very large scale field experiment to introduce the recommender system, and then we'll see the impact of that on things like profit, okay, for the company. Okay, so that's the idea. So I have several research questions. One is, does recommending new categories cause an increase in economic outcomes such as purchase likelihood, revenue, and profit? Okay, so that's research question number one. Number two, when we are giving these recommendations, we have many choices. Okay, I can build, in the particular partner we are working with out here, they have 40 categories of products, okay? So essentially, I can take each user, and for each user, let's say, user number one is shopping in category A. I can score all the other categories for them and maybe recommend them, give them one recommendation, which is the highest likelihood of them to purchase amongst the 39. Or I could give them, let's say, the top 4 recommendations, right? So is giving more choice better? Maybe if you give more choice, your chances of getting a hit increase. But there's also prior research that shows that too much choice is not good. Okay, people get overwhelmed. There may be information overload. So there's kind of like a curvy linear relationship with choice. And so we wanted to test whether is recommending multiple new categories better than recommending a single category. Okay, so we wanted to ask that question, the value of choice. Another interesting dimension with the design of the recommender system is, should we, for example, what is the value of personalization? Okay, so one simple idea could be, for example, just recommend, let's say you are, a wine drinker, and the next most globally popular product is whiskey. Okay, let me just recommend, whiskey to everybody, right? So you don't need any machine learning for that. That's a very simple, common sense type approach. Versus I can build specific models for specific people. I can build a machine learning model that says, no, for your characteristics, if you're a wine drinker, I'm going to recommend Jane. And for somebody else's characteristics, if you're a wine drinker, I'm going to recommend, let's say, vodka. Okay, so that's a personalized approach, and we wanted to see what is the incremental value of personalization? Does that help? Okay, so that's the next one. And finally, I won't have the time to get into this, but we also basically wanted to use a very advanced form of AI now called causal ML, right? Where we wanted to ask whether we can discover subgroups of customers. So for some subgroup of people, maybe on average, maybe adding choice is not that beneficial, right? But for some subgroups of people, maybe they like more choice. Okay, can we discover that? So this one probably we won't have the time to do it. So overall, I have a book coming out from MIT Press next year, which is basically titled "Thrive: Maximizing Well-Being in the Age of AI." So this is the house of AI, where the foundation is data engineering. And in this research, we will use both the descriptive pillar, the predictive pillar, and the causal pillar. Okay, we will use all of these to actually answer a question. So the setting of the experiment, like I said, it's a collaboration with a large online e-commerce platform. It has tens of millions of visitors per year, 40 categories of products. Like I said, 81% of users who have ordered who ordered something have purchased within one category. So of course, the good news here is that the bright side is that there are about 20% of people who buy in multiple categories, and we can learn from that. Okay, so that's going to be the machine learning task. And 88% of users only browse one category. Okay, so for example, let's say you like to buy certain types of clothing, and let's say you like to buy jeans, and let's say another category is kurtas, right? So if you have browsed kurtas, maybe that's a predictor of you potentially liking to buy kurtas, and maybe that's one thing to recommend to you. So that's where some of the consumer journey data will become very useful in designing this recommender system. Okay, and we will deliver our recommendations using email marketing. So the site actually right now does not have any recommender system, unlike Amazon or Netflix. And we will conduct predictive modeling for generating accurate new category recommendations and measuring the causal impact using basically randomized controlled trials, or what you may think of as A/B testing. Okay. So I'll go through this process of generating the recommendations. Okay. And again, if you have any questions, just stop me at any time. So first of all, what data can we use to build these recommendations. Okay, so we did a lot of hard work in what's called data engineering. Okay, so our outcome variable out here is basically a vector of 40 dimensions, whether somebody has placed an order in one category or not. Okay, so let's think of the 40 dimensions as, let's say, different. You go to a store and let's say there's a furniture category, there's a groceries category, there's a luggage category. So these are like the different categories out there. Okay, so if has somebody ordered in a category or not, that's what we're trying to predict. The inputs going into this are a variety of per category indicators. So the number of actions on the product page of each category. On this website, you can customize the product, like you can put your own photo on it. So the number of actions related to customization. Number of actions on the cart page of each category. Let's say you added something to the shopping cart, but you didn't buy it. Number of opened or clicked emails of the particular category. So we're tracking that. How many units did you order of? So the number of orders from a category. How much did you spend? The weeks since the last time you visited that category. Where did you come from? Like where did did we acquire this customer from Facebook, from Google, from Groupon, and so on? The medium visiting, where did the visitor originate from? And then for each of these per category indicators, we also created dynamic variables. So for example, we looked at the total session count across all categories over the last 1 month, 3 months, 12 months, and 24 months, and so on, right? So for each of these other things, like for each of these variables, we created dynamic versions just to see if those will help with the models, okay? So there is a lot of features that are out here, obviously, like several hundred features that are out there. So the first thing we do is, we basically do feature selection, right? So we used a couple of methods that are there in the ML literature to, identify which features are actually going to be helpful in building a model. And in the end, we use this wrapper-based method to narrow down the number of features so basically from 346, we brought it down to, something in the range of like 140 features that were important, and we used those in the model. We used a very standard training and test, time-sensitive, rolling window-based training and test, right? So if this is time, use this much data as training and then use this as test and so on. Kept doing that to, again, build the model, validate it, fine-tune it, decide on the hyperparameters. And then in terms of the actual algorithms that we used, the first thing we said was that, let's do some very common sense kind of approach. Okay, let's build an algorithm that just looks at popularity, global popularity, okay, based on the order amount. So global popularity based on the order amount, basically saying that, for every user, let's say you shop in the furniture category, which is the, other than furniture, which is the other category of products that is bought by everybody. Let's just recommend that to you. So maybe the next most popular thing is, groceries. So we'll basically give you a recommendation to go into grocery shopping, okay? So that was basically, so this is a non-personalized recommendation. And it's kind of based on common sense. You don't need any ML, you don't need any data science capability to do this, okay? Then we also designed basically we tested a whole variety of personalized recommendations based on, something as simple as which category have you viewed most? Okay, maybe that's a predictor of what you want to buy. We formulated this as a multi-class classification problem and tried a whole bunch of classifiers. We formulated this in the terms of like a user item rating matrix, and we tried a whole bunch of collaborative filtering algorithms. We tried a variety of deep learning models, like things like recurrent neural networks, LSTM, and others as well. And our metric out here is hit rate at n, right? So if you give 4 recommendations, for example, how many do we get accurate? How many do we predict correctly in the holdout data set, right? So far we were using very standard machine learning based approach, and what we found was that the global popularity with the order data If we give only one recommendation in the test data set, that's about 28% accurate. If we give 4 recommendations, that jumps up to about 72%, right? So not bad actually. So this is again very simple common sense approach. And then amongst the different types of ML that we built, turns out like the XG Boost, so basically using the consumer journey data to formulate this as a classification problem turned out to be really beneficial. Okay, so basically this was the best performing algorithm. So in the end, we decided, okay, these are the 2 best. So this is the best non-personalized algorithm. XGBoost is the best personalized algorithm. And let's take those and then design an A/B test and deploy these algorithms in the field and then see whether we get additional sales, additional revenue, additional profit, and so on. Okay. Any questions? Is it clear what we're trying to do so far? Yeah? Okay, good. Let's see what's the... So, now we get into the causal part of the analysis. Okay. So basically, again, the reason to do this is that a lot of the ML literature would stop here, right? They would basically evaluate these models on holdout data and then they're done. But that was not good enough for us because it does not tell us the causal economic lift of this. And so to understand that, we have to design an A/B test. So in this case, the way we designed it was that there was we took the existing users that we had, we randomly split them into 1, 2, 3, 4, 5 groups. There's a control group that was left as it is. There is a treatment T1. These are people who are given the one recommendation of the most popular product that they have not bought. Okay. T2 gets top 4 recommendations of the popular products that they have not bought. Okay, so difference between T1 and T2 is basically we're still using the popularity algorithm, but we're going from 1 to 4. And then 3 and 4, we give 1 personalized versus 4 personalized. Okay, so people are randomly assigned into one of these 5 conditions. Okay, and we deliver these via email. So basically, for each person, we send, we took over their email marketing for that week, and we send them these personalized emails, right? If you got 1 category recommendation, it was basically, this kind of a setting. If you got 4, it looked like this. So very clean experiment design in that sense. And to quantify the economic impact of, let's say, giving a recommendation or not, right? Remember, the first research question was, is there a causal economic impact of giving a recommendation? Basically, what we are interested in is, we have a control group. So relative to C0, relative to this group, right? What is the incremental, let's say, profit from T1? Okay, or what is the incremental? So that's basically what this coefficient out here, this beta 1, will tell us over and above C0, how much incremental, let's say, sales do you get from T1, and this will tell us from T2 and T3 and T4, so on, right? The other variables are just control variables. Even if you remove them, we don't get any different results. We get the same results, okay? So let's look at our results. And by the way, so this is for research question number 1. Question number 2 was, does choice help? Okay. So for that, what we do is now we will make T1. So basically now the control group we can only include the data where somebody got a recommendation, and the question is, what type of recommendation should we give them? So the control group now becomes T0, the baseline is T1, sorry, and T2 will tell me for the popular recommendation, what is the value of choice, okay? T3 will tell me so T3 is 1 personalized and T1 is 1 popular. So T3 will tell me what is the value of personalization, okay? And T4 will tell me what is the value of personalization and choice, okay? Beta 3, this coefficient, beta 3, okay? So beta 1, if I estimate this regression, beta 1 will tell me the value of basically adding choice to popular. Beta 2 will tell me the value of adding personalization. And beta 3 will tell me the value of adding both personalization and choice. Okay. So let's skip this part, randomization check. Let's look at the results. So does giving a recommendation have a causal economic impact? The answer is actually yes for all the three outcomes that we cared about: purchase, likelihood, will you purchase or not, your log of revenue, and log of profit. Okay, and the effect sizes are pretty substantial, right? So essentially, what we find is that, for example, if you look at profit, right, you have a 44% lift over the baseline if you give a recommendation or not. Okay, 54% lift. So from T1 to T3, you start seeing a pretty significant, causal effect of giving this recommendation out there. Okay, so this is very encouraging. So then we wanted to look at also, what is the value, for example, of, let's say, adding more choice. Okay, so going from 1 to 4 looks like there is some incremental value out here. Okay, also personalization from 1 to 3, personalization also has significant positive effect. And so multiple recommendations lead to significantly higher purchases. And so that's good. Okay. Personalized recommendations also lead to significantly higher purchases, revenue, and profit. That's good. Okay. However, what is interesting is that conditional on personalization, right? So if you look at, for example, if I do T4 minus T3, right? So T4 minus T3 basically is, T4 is 4 personalized and T3 is 1 personalized. Okay. So conditional on, so these are p-values. So statistically, they tell you whether the difference between T4 and T3 is statistically significant or not. And remember, we want these p-values to be 0.05 or less to claim whether it's statistically significant. And what we find is that if you're personalizing, right, so with popular products, adding choice helps with popular recommendations. But if you're personalizing, there is no additional value. In other words, the ML algorithm is able to, suck out the information from, so just giving 1 recommendation is as good as giving 4. Okay, for once you personalize. So that hard work of personalization gives you the benefit of reducing choice. You don't have to give 4, you can just give 1 and you can get the same kind of outcome out there. Okay, so Asif, how am I doing with time?
Yeah, I think another 10 minutes.
10 minutes? Okay, yeah, okay, yeah. So that's the main takeaway. So basically, in terms of results, basically we find that adding choice helps, adding personalization helps, but conditional on personalization, adding choice does not help actually. Okay, does that make sense? Okay, why? Because the ML is able to pick up the signal, and you don't need to give 4. Whatever information is there, you get it in the best choice itself. Okay. So this is the main set of results. Maybe what I'll show you a little bit next is that there is now a whole new area in ML called causal ML. Okay, so in this case, you saw we built a whole series of machine learning models initially to pick the best one, which in this case was the classifier actually, using rather than those deep learning models or the collaborative filtering models. Formulating this as a multi-class classifier using the customer journey data was the best way to go. We tested that using an RCT, right? So did an actual A/B test in the field, and we found that. So once most papers actually kind of stop here, we wanted to go further. Okay, so what we did then was we said that, okay, how about we look at the data from the treatments and see if we can figure out a way to personalize the recommendations based on different subgroups of people, And this is a whole area called discovering heterogeneous treatment effects. Okay, and there are algorithms like the causal forest algorithm that allow you to do that. So we built a causal forest on the data from our experiment, and we found that the top 3 features that showed up in the causal forest were basically the log of the last visit time. So that's like a recency metric. The log of the actions on the product page. So that's like an engagement metric. So recency, engagement, and your order. How much did you order, right? So we said, okay, these are the 3 most important features in discovering these subgroups. So let's just zoom in on these, and then essentially what we were able to do is, for every user, we are even though, let's say in the experiment, because of randomization, a given user can only be in one of the 5 cells, right? You can, if you're in the control group, you can't be in treatment 1. If you're in treatment 1 group, you can't be in treatment 2, right? But because we have the data for these, we can essentially predict how you would behave. Even though you're in control group, we have the data from, let's say, T1. We can build like what the causal forest model will do is it'll build a predictive model for that particular treatment arm, and then I can take the people who are in the control group and predict how they would have done in the treatment 1 group, and so on, right? So for every user now, I can estimate how they would have behaved in each of those treatments, and I did that, and then basically summarized those individual level treatment effects using those 3 variables, and just describe that using a tree. Okay, so basically what you're seeing out here, for example, is that if your log visit time is less than 0.086, you go here, and if your log of total payment is greater than 0.46, you come here. You see this is a highly positive. This subgroup of people, this subsegment, responds very well to choice. Okay, and similarly, you can find subgroups of people. Notice that there is a subgroup of people out here that respond negatively to personalization. The treatment effect is minus 0.1. Okay, so these are people whom we do not want to give the personalization of. Okay, so we can discover. So the whole idea is that we can use machine learning to now personalize the delivery of the treatments using this causal forest approach. Another way to look at the same things is I just take the data and I do a heat map. We plot things like last visit time, percentile versus the total product order page. Okay, and this is for choice. And the ones in red are the ones that are really positive, and the ones in blue are where you're losing money. Okay, so this segment of people who have a certain type of frequency of purchase, but who are high spenders. Okay, these are people who I do not want to give. So it's negative, basically. I do not. All the light blue ones are all negative. So these are people who I do not want to give choice. I can similarly visualize, recency of purchase versus order payment. So this is recency and engagement, recency and the amount spent. And we can find the red zones and the blue zones. So we target only the people with the red zones with a particular type of treatment, right? And then similarly, if I look at personalization, I find different segments, right? So for example, these are blue. These are people who we do not want to give personalization. Okay, the reds are the ones. Those are so this is a segment of people whose percentile of the recency is like between 5 and 10, and the percentile of how much they spent is in the 80 to 90 percentile. And these are people who are very positively responding to personalization. Okay, so these are actually just shows you, like, if we use this causal forest approach, like how much more lift we can get, as opposed to just giving everybody the average treatment effect. So in conclusion, in this study, what I showed you was how to use machine learning methods to design recommendations for types of tasks where we cannot use typical like collaborative filtering algorithms because we don't have that kind of data. We don't have a user item matrix. So what we showed is the value of using very rich, consumer journey data. And what we found is that recommending a new category to existing customers increases the new category purchases as well as revenue and profit. So we can say this with confidence because we ran an A/B test to prove that. We also found that providing multiple recommendations and personalized recommendations further increases new category purchases. However, conditional on personalization, you don't need to give multiple recommendations. And then, we did what's known as HTE, which is heterogeneous treatment effect analysis, to find, that can help us personalize these treatments. Okay. So, any questions?
Sir, could you elaborate more on the causal ML aspect?
Yeah. So the causal ML, basically, the algorithm that we use out there is causal forest. So the basic intuition is that, in the experiment, people are randomly assigned to one of the 5 treatment groups. But theoretically, you can think about, each the data that you get from control group and the treatment 1 and treatment 2, you can build a predictive model using that data. And let's say you were in the control group. Now, if I have a model for how everybody in general behaves on treatment 1, I will predict how you did in treatment 1, right? So I can overcome this limitation that you were only in one group by predicting how you do in T1, T2, T3, and T4. So now I know, like for every person, I can basically say that, okay, this individual is responding best to treatment 4, right? And then the rest is just, understanding that data a little bit better, describing it and so on, okay? So that's what the causal forest algorithm does in an efficient way, okay? So yeah, so it's by Susan Athey and others. Yeah, good question. Any other questions? Yeah.
Why did you use only 4 items? Is there any significance to it?
Yeah, good question. So, in the real world, you can't, because that's how the company ran the email marketing, right? So they typically would send these 4 pictures, in a typical email. So ideally, we would have liked to test like a continuous spectrum, like, maybe like all the way from 1 to like 8 or something like that. But that, because it's a field experiment, the practical limitations prevented us from doing that.
And the 4 items you recommended, were they of same category or different category?
No. These are different categories. So these are all 4 different categories, right? So this is, and remember, we're not recommending items. We're actually basically sending you to the category, right? So let's say you shop in furniture. Then you would get this email. This would say, it would be basically a picture of the groceries page. So we want to send you to the grocery homepage. Or you shop in furniture. So maybe the most likely one for you is grocery. The next one could be, let's say, clothing. This could be luggage. And this could be something else, right? So we will send you to that page and then you do whatever, and then we track your outcomes.
So,
Yeah.
you chose the one is the most popular category, the other is personalized. Can you go back to like how you decide how you make the personalized category?
Oh yeah. For that, we tried all these. These were all the algorithms that we tried for personalization, right? So we formulated it as a classification problem. We tried a whole variety of matrix factorization methods. We tried a whole variety of sequential methods, like basically popular link. So think of popular link as like association rules with some sequence information, like recurrent neural networks, LSTM, and others as well. And so that's basically how we got to the personalized recommendations, right? So these are all the different models that we tried, and the XGBoost model was the one that was the best. So that's what we ended up using. Yeah, it's not typically used in recommender systems problem, but because this data set, it's not a typical recommender system situation. We can't use, so for example, the collaborative filtering type algorithms like these two, did not do really well. Deep learning models did not do really well actually out here. All right, thank you very much. Yeah.